and officially open this webinar on vector symbolic architectures, VSAONLINE. And this will be the last webinar of this season. So now we are close to Christmas break. So I'm happy to host Yeseong Kim today. So without any further delay, so Yeseong, the floor is yours.
Yeah, thank you. Thanks for the introduction. I'm Yeseong, as he talked about, and I'm from DGIS, that's South Korea. Today I'm going to talk about the long title, but basically it is about the how to use the hyperdimensional computing or vector symbolic architecture for robotics task. This work is supported by the Cobra Robotics, the robotics company in Korea. Before going to talk about the technology details about our framework, I'd like to first chat about what is the AI. Basically, when we are talking about the AI, then we probably imagine the ChatGPT or diffusion models that may make some of the images. But if I ask the same question to my daughter, 5-year-old age, she would say it is worry, right? So basically, traditionally, when we are talking about the AI, it is the combination of the robotics plus some of the intelligence. I can give some of the more evidence, like some of the old movie back then, the early 2000s, or it could be another movie like more recent movies. But everything, when we are talking about the AI itself, then it is about the robotics with the intelligence. I'm from the computer science, so I'm not really good at the robotics itself, but I had a chance to develop those hyperdimensional computing algorithms based on the 4D robotics by some of the chance. So I'd like to talk about those stories. So when we are thinking about the computer or AI technology trend, all of us are familiar with the Moore's law. So the number of the transistors in an IC chip, it doubles about every 2 years, and it stopped like 10 or 20 years ago. So, but when you're thinking about the size of the models for the modern AI, like the deep learning models, like transform or other architecture, the number of the parameters in the deep learning model increased 10 times per year. So basically, it means that there are some of the huge gaps between the computing capability that we can provide versus the amount of the workload that we have to handle for the AI task. So imagine that the future of the robotics, probably there are some of the paradigm shift that may happen in our AI trend, like we saw some of the huge jump for the AI technology for the last 10 years. Probably for the next 10 decades, probably there are some of the changes for the robotics as well. So when we are talking about the AI paradigm shift, nowadays, main things are really running on the cloud-based. There are some data center, there are a huge amount of the GPUs, and we can do some of the computation on there and getting the result from there. But when we are making it really compact, then we may think about the tiny AI stuff. Like we may do some of the quantization or pruning. So basically, we are tuning the deep learning models to make the more compact. Probably it would run on the small device. But when we think about the robotics, it should be much smaller. So when we are talking about the micro AI, for example, then it should have the general learning capability for the artificial intelligence. And it should run the information online with some of the fast or efficient capability. And it should be very hardware friendly, of course, because we have to make the chip very compact. Otherwise, if we can follow those trends, in the future, then probably the future would be a little bit sad, right? So if we are thinking about some of the robotics in the world, joyful world, but in the another side, it should be a rest of the buildings that runs the high performance computing task by consuming lots of energy. So to fix those problems, we have to draw inspiration from the brain. Probably all of us attending here are fascinated about this concept. So when you're thinking about when you're recall the old code game from the Google DeepMind, when the AlphaGo runs, it uses the latch of the CPU and latch of the GPUs. Like CPU is around 2,000, and there are some of the 3,300 of the GPUs, and there are many scientists behind there. But if we think the brain efficiency from the researcher, then it would be some of the brain, coffee, or tea, or some of the meals, and it only need 100 watt for the whole body. If we are only consider the brain, then it is the only 20 watt. So basically, we want to mitigate those gaps between the current computing technology and the human brain. So if we think about what is the characteristic of the brain-inspired computing, then it is quite fault-tolerant, and it has the learning ability. It can be happen supervised or unsupervised way, and most importantly, it is really using the low power, right, 20 watt, and it is really high parallel machine, and it is also extremely compact. So there is no reason to follow those principles to build the new intelligence. I'm not really going detail about the hyperdimensional computing on here. Probably most of us are really expert on this, but in a nutshell, it is following those things, right? So if we have the raw data in one side, then we are doing some of the encoding on there, so that we can represent the information using the hypervectors. And with the hypervector, we do some of the cognitive operations like memorization, reasoning, or association or search. Then by combining those things like those bundling or binding operations, we can build the learning algorithms. So for the last decade, many of us are really working for those learning algorithms so that we can meet the standard, the global standard of the machine learning. So the examples are classification, clustering, regression, reinforcement learning, or recommended systems. Then our focus was how we can realize it for the robotics. So actually, there was some of the personal background story why I'm doing those things. So when I was asked about what is hyperdimensional computing or where to use it, then I always said, okay, there are some of the gaps for the accuracy, or there are some of the story that makes the efficient, but we need some of the proof how it will some of the proof of we can really use it for the real world. And one of the obvious example is the rope, because it is really running on the small device. So that was the story of the why I'm doing these things. So for the typical example, or for the classical example, we can draw the HDC classification procedure like this, right? So when we are having the original data, we are doing some of the encoding, and then we are doing some of the linear types of training, like bundling or binding. Then we do some of the simulated search for the inference. Then if we do the same thing for the classification task, then it is one of my favorite example. There are some of the concept of the catch, and if there are some of the concept of the dogs, then we can make the hypervector by doing the encoding and training. And then if we have the another new data, then we do the same encoding and check the similarity search on there. So we are what our group did was we are moving those concepts to the robotics. So I'd like to briefly introduce how the robot really works in the nowadays. So traditionally, for the robotics task, there are two different pipelines. Like for the first piece is the perception. So we are getting some of the information from the sensors. Like we can use a LiDAR to get the distance. We can get some of the images using the camera, and there are different types of camera, like depth camera. And then by doing some of the computation on there, and traditionally it is really high engineered, and then we are making some of the actuation for this one. So for example, if we have some of sensor input like this one, basically we do some of the actuation, like we do some of the controls for the robot motors, or we can do some of the controls for the servers to make some of the angles. So basically, we can map those concepts by replacing the middle piece with the learning algorithm. So for our design, what we did was we want to find automatically what is the relation between the perception and actuation. Basically, for the traditional robot controls, it is like some of the rule-based algorithms. Like if there are some of the LiDAR shape like this one, then we can make the actuation for the motors like this. There are some of the relationship between those perception and actuation. So what we did was we are making the HDC model for the perception to action, so that we can, if we get some of the sensor inputs, then we are doing the encoding, and then we are checking the similarity for the action hypervectors, and then we can select the suitable actions for the robot. And that's the all of the stories. So here we call those techniques as a React HD. So it is one of the HDC-based framework for the robotics. So here is the overview of our framework. So basically, the goal is we want to learn the robot controls based on the brains called hyper-imaged computing. So let's think about this one. So we have the robot on the left side. Then originally it collects some of the information. And for this work, we focused on the LiDAR, which measures the distance for different degrees. And then by encoding those one into hypervector, it means the perception hypervector. Then we are doing the two different things. One is the supervised learning, and by supervised learning, so it is kind of realizing the imitation learning. So if the expert doing some of the actions for those different situations for the LiDAR input, then we are learning those patterns with the classification model. And the other option that we can do is the reinforcement learning. Basically, it is the some DQN-like reinforcement learning model, but all of the piece learning behind is based on the HD computing. And then by using those two algorithms, we can make the perception to action model so that we can do some of the actuation selection based on the current input of the LiDAR sensors. And to show the effectiveness of our framework, we perform different tasks like the obstacle avoidance or object tracking or navigation. And all of them really works well in our framework. So I'd like to show the examples of this one during my talk. I'd like to describe what is the real-world robot that we are using. So we use the two types of the robot. On the left side, it is the omni-driving robot. Basically, we can move the robot for the different directions quite freely. But for those work, we choose the 8 different angles to move. And this is the main robot that we are using. The second type of robot is the black one. Black one also have the LiDAR on the top. So we can measure the distance. The input is basically same, but it is using the different controls. To move in a one direction, it has to rotate first, and then it can move on those direction. So, but basically, there is the some of the actions that we can choose, like we can control it like pressing the button, like left button or right button to rotate it, and we can move back and forth with the corresponding arrows. But for our the final demo, I was using the first type because it has the larger space to choose the actions. But although it is discrete, probably it could be continuous in the future. But in the current version of our framework, we are using the discrete. And what is the input? So the control is control is the motor controls. For the perception, it is about the LiDAR or camera input. But for this work, we want to only use the LiDAR because of the real-time response. So when we draw the data gotten from the LiDAR sensor, then it looks like this 2D projected image. So we can do some of the simple math to get those images. Like from the center, we can measure what is the distance around there. So if it is located in a box, then it will look like this. But in a raw data, because we want to use the raw data without using any of pre-processing step, so the raw data looks like the right figure. So there are some of the continuous input, like it is basically the measure for the distance for the different degrees. So we are using those input as the raw data, and we want to encode it to the hypervector. So for the LiDAR data encoding, we borrowed the idea from our old work. We call it STEM encoding, spatial temporal encoding method, published in the math code. So the idea is instead of making the different hypervectors for each input, because the LiDAR sensor input, if we say the one measure of the distance, this distance value has some of the relationship to the close point, right? So for the LiDAR input, it is measuring the different angles. So there are some of the angles which is really nearby for one sample. So to keep those relationships into our encoding method, we make different hypervectors that represent sufficiently far distance, far angles. So for example, if we have the 300 input around there, then we can say that the first input and 10th input is really different. Then we can make the orthogonal hypervector on there. We can interpolate the middle point. We can interpolate those two hypervectors for the middle point data. That's the idea of the use in the encoding. And so if we redraw the raw data inputs on the left hand side, then basically we are mapping the different inputs by keeping their similarity for the close point and differentiating the meaning of the different samples which are far enough. And for the actual encoding, that's what we are doing. So because the LiDAR has the kind of circle, right? So the degree of 0 is same to the 360. So because there are some of the rotating relationship for the data point, we are making the hypervector based on those relationships. So basically, the first hypervector is used to represent the first data point and last data point. And then we can do some of the interpolation between them by making some of the partitions for the data samples. And then because we want to keep the temporal information, like the LiDAR input is keep coming, like around, we can get 100 samples per second. So because we want to know how it is really changing over time, so we can get some of the n-gram style encoding so that it can really, so the encoded hypervector eventually represent the positions of the one timestamp as well as the movement of the robot coming from the LiDAR. That's the encoding method that we are using. So, so for the training phase, we have the two different components, as I talked before. One is the imitation learning, basically the form of the classification task, and the other one is the reinforcement learning. So I'd like to talk one by one throughout my rest of the talk. The first one is the imitation learning. Basically, it is the classification task. So what we did was we first does the data collection. So we collect the LiDAR input as shown in the left side. So we collect the different data points for the LiDAR input, and while getting the movement or the motor controls by the expert. So he is my student, and he plays the robot multiple times. And then we use those collected data as a training data set. So obviously the goal is to make the precision to action model for the simulated search. And by changing, one interesting thing is, by changing the training data set for the different tasks, we can do the different robotics task without changing any internal code. We just need to replace the HDC model to accomplish the different jobs. So here is some of the idea that we add for our framework. The first part is the hard negative mining. For the real world robotics task, there are lots of hard negatives. For example, let's say there are some of the tasks like the object avoidance on here. Then usually robot is not really moving. Robot need to move when the obstacle is coming close. So there are lots of the case that robot has not to move, while there are some of the special cases that robot need to move for some of the data sets. So to reflect those characteristics in our training framework, we do some of the hard negative mining. So basically, what we are doing is we are memorizing all of the hypervector encoded for the training samples, and we make some of the weight. And for first, at the initial stage, the weight is really equal for the ultra samples. But once we do some of the training using the classification notation, like we do some of the bundling for the one iteration, by checking the similarity, and we can find what is the what is the correct class and what is the misclassified class. And if it is misclassified, then we are doing some of the bundling for the correct class, the typical story of the HD training. We do this one, we do this training process for the one iteration. And then we re-evaluate all the training samples so that we can get the weight for the samples. So if, for example, if one of the sample has the lower similarity to the desired action hypervector, then it means that we have to have the higher weight so that it is considered more for the next iteration of the training process, right? So we do those hard negative mining so that we can make the different data set for each training iteration, so that it is converging to the some of the good model that can really recognize the hard negative cases, while it is do some of the special instruction of the movement for the our target scenarios. That's the imitation learning that we are doing. And I'd like to show some of the videos how it really works. It is the task of the object tracking. So basically the goal is to follow the human over there. And it works quite well. And the interesting is the training is super fast. So for those tasks, I think we just record like 1 minute, 1 minute recording for the LiDAR and auto control, and it works quite well. And I'd like to show the second example. We call it navigation 1 task. It is kind of rotating those boxes from there. And we only record like 3 times the circles. And it works also quite well for the imitation learning. Imitation learning really fast, and it is really reliable using the hyperdynamic computing. And intuitively, it is really makes sense in terms of the HD computing, or vector symbolic architecture. We are basically checking the similarity between the input and output. So as long as there are some of the similar inputs into our training data set, we can do some of the similar jobs in the real world. It is the more complex task. So there are some of the different engineering for this one, but we are doing the same thing we are doing the same training procedure to solve those problems. And there are some of the LiDAR measures to check the distance between them. And then it is eventually finding the core from the starting point. So it really works well, and it was really great. So I'd like to move to the next technique that we used, the reinforcement learning. So for the robotics work, reinforcement learning is really important. And interestingly, there is some relatively small number of jobs. I mean, in the literature, some of the people are really investigating the reinforcement learning for the robotics, but it is not really huge volume. That's what I talk about. For the reinforcement learning, it is important in the robotics domain because robot is not safe. So if we are driving actual robot in the world, then if we are applying the reinforcement learning, basically doing the trial and errors, then the problem is robot would block hit the wall or hit some of the obstacles. Then it is not really good for the continuous running. So what we did is we make some of the evaluation framework for like gym style, reinforcement learning gym style. So I'd like to show the videos like this one. So basically, it is kind of the mimicking the real world by placing some of the obstacles over there. Then we can check, we can translate those environment to the virtual LiDAR input that considers what is a noise and what is a distance. Then we can get the realistic input for the LiDAR in a simulated situation. We collect those information as a training data set. And then our algorithm is interacting with those environment to get new samples every time once the reinforcement learning agent decides the action. And the outcome is same with the imitation learning. So basically, it finds the model. So once it is trained by reinforcement learning or the imitation learning, we are getting the same format of the model so that we can deploy into the actual robot. So yeah, here is the entire framework. It it is really similar to the DQN style. There are some of the publication from our group and my friends, the Mosense group. There are only few work for the reinforcement learning, but we can make the reinforcement learning like in a DQN style. So basically we are during the training procedure, we are making two different models. One is the model that estimate the Q value using some of the regression based on the hyperdimensional computing. And we also keep different model, the target model. So we are making these two different models to stabilize the learning process. And then we do some of the similarity computation to the desired reward that we collect from the virtual environment. So if we do some of the navigation tasks, then the reward would be if the virtual robot cross the line, then it means that we can get some of the partial reward, and it eventually get the higher reward at the in the location of the goal. So we are getting those rewards, and we train the situation that we can get the higher reward. Then once it is trained, then the HDC model, the Q value model, is eventually the model that you have to deploy in the real world robot. There are another thing that we add for those story. The story is the prioritized experience replay, which is located in the left box in this figure. So what we did is quite similar to the hard negative mining. So basically, we are getting some of the weight. We make some of the priority for the training samples. So if there are some of the samples that is hard to classify in the current model, then we prioritize those things with some of the weight, so that we can get the mini batch of the training samples every time for the different set. So basically, we are random sampling with some of the weight, so that we can get the samples which is hard to predict with the current model. So by adding those stuff, we can train the reinforcement learning model, and the result looks like this. So it is the another task. It is avoidance. So avoidance is a little bit different from the tracking because avoidance has lots of hard negatives, which robot doesn't nearly move. So it is quite running well with the reinforcement learning, and we can do the tracking task in a similar way. The different from the imitation learning is there is the interaction with the human expert. Everything is really automated. It is just randomly moving every time at the initial stage. But by doing some of the iterative running using the reinforcement learning procedure, we can get high quality model at the end. It is the same task for the navigation one. It is rotating the box, and it works quite great. Interestingly, there are some of the mistakes at the beginning because the reinforcement learning is not really well as compared to well behaving as compared to the imitation learning, because it learns the trial and errors. But after some of the trials, the robot is going here and going outside because it is close. It learns those patterns, but because it is too far, it is coming back. Okay, so it is quite interesting, It is learning some of the procedures that the expert may not do in the training process. So it knows different scenarios, and then it is kind of the proof how it really runs internally. It is the final task. At this moment, we are making some of the works over there because for the reinforcement learning, we have to make some of the boundaries so that it quickly converges to the final course. And it is not really fast, but because of the low speed, but it looks quite well. You find the target course starting from the first location to the end goal. So it was quite cool. Yeah. So I'd like to give some of the result. I showed the demonstration of our robot, but I'd like to discuss what is the efficiency that, or what is the advantage we can really get by deploying those hyperdynamic computing into a robot. So for here, we use those the omnidirectional robot, so it can move toward any direction. And the computing source or computing device for this robot is Raspberry Pi. So it doesn't have any of the GPU. Everything is running on the CPU, the ARM Cortex A72, which is quite low power, as you guys know. And for the LiDAR input, it gets 720 data points per scan, which means that there are some of the 5-degree granularity between two consecutive measurements. And the scale frequency is around 8 to 9 hertz. So for each second, we can get around 100 samples. And we can do the encoding procedure that I talked about, like we encode one data point and we bundle different data point so that we can make the hypervector that we have to consider at the current moment. For the implementation, we use PyTorch. And actually, I think we can make it better by replacing, because the PyTorch is not really optimized for the binary operation. Lots of things that happening in our framework is really binary. So probably by doing some of the better engineering, like we can do some of the parallel, computation for the arithmetic operation for binary data type, we may do better. But even though there is no sophisticated stuff for the programming engineering, it is quite working well. And I will going to show some of the graph, like efficiency or accuracy, and I use those acronym for the different tasks: AVO, avoidance, TRA, the tracking, and navigation 1 and navigation 2. Here is the accuracy comparison. So what we did was we compared it with the baseline approach, the baseline HDC approach, and there are some of the difference from our method. There is no hard negative mining. We can apply that. The sky blue color is the accuracy that applies the hard negative mining. But there are the different stuff. One of the most important thing is the encoding method. Instead of doing some of the binary only encoding, we are doing some of the circular types of encoding, like we want to keep the similarity in a close data point, and that makes really work. That makes the difference. So for the accuracy, it outperforms the baseline HD approach because thanks to the hard negative mining and the new encoding method. Plus, if we compare the accuracy with deep learning, which doesn't really use those, the circular types of encoding, it quite works well. So I would say the accuracy of this one is quite comparable to the deep learning. If we consider some of the characteristic, inherent characteristic of the LiDAR input. So yeah, that's the thing. And there is one of the weird 3 bars on the right-hand side, the 3 red bars. We are testing this algorithm with all the literature for the HDC-based virtualized simulation for robotics, but the test case was really simple. So our goal is to make it realistic in the real situation. So we want to compare it with the old method. And when you are comparing it with, it also works well with the simplified situation as well. Here is the result of the efficiency. So I'd like to talk about mostly the speed up. So because we use the Raspberry Pi, we can say that everything is running on the CPU. So when we run the deep learning model on the Raspberry Pi, the improvement is around 14 times. So for the imitation learning training procedure, it is 14 times faster than the deep learning. And for the inference, more or less the same efficiency for the inference. For the reinforcement learning, it is a little bit slower. It is still outperforms the deep learning performance for the training, like it is 5.3 times faster. But because the reinforcement learning is kind of the interaction with the simulated environment, so there are some of the overhead over there. So because of this one, we cannot really get the highest efficiency as we did for the imitation learning, but it is still quite okay or quite good. If we talk about the model size, it is obviously small because we don't really need to store all of the deep layers for the deep learning models. Yeah, that's the thing. And it is the last slide that I have. So I'd like to show what happens in the real training. So at the left-hand side, it is the actual environment that we tested. And it is the training, how I can say, the heat map for different epoch. The middle of the figure, the middle figure is what HTC model runs for the initial epoch. So it looks like it works quite well, but you can see that there are some of the errors across the border or walls, which means that if we run this model, then it is moving, following the path, but sometimes it hits the wall. But by doing some of the iterative procedure for the reinforcement learning based on the HD computing, we can make the more accurate model that really push the ports from the wall side so that it can really make some of the guideline for the path so that the robot move correctly. So that's the thing, quite interesting result. So I brought here. Okay, that's the end of story for today. I'd like to conclude my talk. So we applied the HD computing for the robotics task, and we proved that it is quite effective and efficient learning solution. It can run on a very small and low power device, enabling the online learning. And we do some of the imitation learning or reinforcement learning, which are discussed in literature for the scientific research papers, and it is really working well for the real world. I'd like to have a quite small advertisement. The company that funds this project is we decided to make a new venture called UNAI. So basically, the goal is to make the commercialize for the HD platforms. Probably we may do some of the sensors or controls. Basically, we can make some of the computing platforms for robotics. Let's see what happens. Probably it will happen next year. I think that's all for today for me. Do you guys have any question? I'm happy to answer that.
Yeseong, thank you very much for your talk. Thank you indeed. So now I open the floor for questions. So let's see. Please unmute yourself and speak up. Maybe I can start with the question. So it's more on methodological side. So when you present comparison in favor of HD, so why are you comparing to CNNs, like to deep learning? I mean, because to me it's not really a fair comparison. So because I mean, maybe deep learning is not a suitable architecture in the first place for this task.
So basically, the reason is quite obvious because everyone asks us. When you are talking about the new learning algorithm, then they are asking, do actually what is different from the deep learning. That was the first thing. But the other thing, the other actual scientific reason that why we did was because we want to compare this algorithm with some of the sophisticated algorithm, state-of-art algorithm for this one. So, and I believe there are some of the interesting characteristics for the vector symbolic architecture or HDC computing. Like it is really lightweight because there are lots of binary operation. We can make the really good quantization on there, to prove, to show those effectiveness, I think one of the good way was to use the deep learning, the state work. Probably we can compare it with the more sophisticated robot-based controls like traditional and hard, the real engineered the algorithm for the robotics. But the thing is, probably it is quite good approach, but the problem is that the robotics control, nowadays is really complicated. So, for example, if we do some of the object avoidance, then we have to do some of slants. It is getting it construct all of the field from the sensor input, and it is really slow. So I think it is not really good way to compare it. So probably that would be fine, I believe.
Okay, thanks. Other questions? Let's see.
I have one.
Yeah, should.
Yeseong, I have a question, more conceptual question. I don't think I've ever fully appreciated the advantage of doing reinforcement learning with HD computing. Could you please maybe reiterate again the points on these ideas, what is catch about doing reinforcement learning algorithms via HD computing?
So I like to talk about two different things. Let me show the algorithm part over there. So actually, it is really similar structure with the DQN style model. So you have the dual model, and we do some of the value-based policy. So we do some of the regression with the HDC model. So basically, all of the things are same, but the difference is many things are happening on there is really bundling or binding stuff. Most of them are really bundling. So we just do some of the addition on there, to update the model. And I didn't bring this result from the slide, but let me find out one of the slides from my folder. Let me pause the screen sharing to answer this. What I saw was when we are using the HDC for the reinforcement learning, sometimes it is super fast as compared to deep learning. I don't know what is the underlying result. Probably it would be attributed by the characteristic of the fast runner of the HDC. But we didn't really get into the technical analysis on there. But here,
and when you say fast, that it means that the model starts working fairly well, very quickly, right?
Yeah, it is learning quite fast. So yeah, so I think it doesn't really have those results. Probably yes. No, it doesn't have those results. But usually it is not really always. So it is a little bit hesitated to say HDC really outperforms all of the fast learning stuff for the all task, but for the around 70 or 80% of the tasks that we tested, HDC runs much quickly than the state-of-art reinforcement learning based deep learning. So probably it would be it would be the point that we have to analyze for the further development. Yeah. I think this graph is comparing the result with the prioritized experience replay and without this one. You know, the prioritized replay makes the learning really stable and quite fast.
All right, got it. Thanks a lot for the clarification.
Thanks for the question. Yeah.
Anybody else want to ask Yeseong? So let's see. Ross unmuted himself.
Yeah, hi. A question about the circular encoding for the LiDAR data. So if I understand what you're doing, you've got a number of directions that you assign vectors to, and then you interpolate angles between those. So then the similarity would scale linearly as you move between the prototype direction vectors. So my question is just, how many of those prototype vectors do you have? So I mean, how many degrees apart do things need to be on your LiDAR for the similarity to go down to 0? And how did you arrive at that particular figure for your work? So did you experiment with different bandwidths of that similarity kernel?
So for the those partitions, so basically it is related to the number of partitions, right? So how many orthogonal vectors really need to represent all of the 360 degrees. So what we used is we grouped 10, right? So there are if the difference of the angle exceeds the 10 interpreted as 50, so if it is exceed the 50 degree, then we assume that they are far different, or they are sufficiently different from each other. So, so basically, what we first tried was we are making really pseudo orthogonal vectors for each of the data point at the very first time, but it doesn't really work well because there are really lots of noises. If we make those, partition hypervectors over there, which covers like 50 degrees for each partition, then it smooths out the noises as well as it is really good to find the similar patterns for the LiDAR data.
Yeah, I mean, with the some of those partitions don't actually need to be distributed evenly around the circle.
Yeah.
So with that, with the robot you were using in the in your videos, that's the one that's the omnidirectional robot, so it doesn't really have any sense of front. But whereas the other robot that you didn't use, it actually has a straightforward direction, so you could have a if you're doing if you were doing the right tasks, you could have perhaps finer angular resolution in the forward direction and have less resolution in the behind you, where you just foveal resolution in the eye.
Yeah.
But so it'd be interesting to see how much different tasks depend on the trade-off of the, as you say, the smoothing out of the noise and the actual accuracy of what you're doing.
There is one thing that I missed in my presentation. Actually, there is one more thing that we did for the imitation learning. What we did was we call it the data augmentation. So basically, when you are getting the input and output the pair, then we are doing some more rotation to the input so that it can make another angle data automatically. So it works quite well for those types of stuff. So yeah, but we really didn't do it for the reinforcement learning because our goal is to make some of difficult stuff like navigation. And for the navigation, we really because the path is quite deterministic because our simplified problem. But for the actual your data set, like if you want to make the different route or for the multiple angles, then probably those data augmentation or rotating stuff would be quite valuable to make the high accuracy.
And that would depend on the task that you're doing. So, I mean, if
Yeah,
you
it
had, for
depends.
example, some sort of a robotic arm on the front of the robot, then if it had to manipulate small objects, then you'd want higher resolution, presumably, to do that.
Yep, I agree.
Okay, thank you.
All right. I think we are approaching the limit for today's webinar. So all other questions are welcome online. And the only thing what remains to say is that this was the last webinar before Christmas, so I prepared the special hat for me. So maybe I will be one of those who will spread Christmas wishes early this year, but in Sweden it's normal. We already started the Christmas holidays. So I wish you happy New Year, hyperdimensionally happy New Year, and Merry Christmas. So I'll see you next year. So if you have topics to present, so you know my email, so please send me a note. But otherwise, so I'm sure we will be able to construct an exciting program for next season. So have good holidays and see you in 2024. Thank you all.
Thank you. Bye-bye.
Thank you. Bye-bye.
See you later.